Have you ever wondered why, in the vast cosmos, everything spins yet we feel utterly still? The Earth spins at over 1,000 miles per hour, orbiting the Sun at 67,000 miles per hour, while our solar system races through the Milky Way at nearly 500,000 miles per hour. And yet, in the midst of all this motion, we don't feel a thing. We're going through space at unimaginable speeds, yet our heartbeat doesn't quicken, our breath doesn't sway. The coffee in your cup doesn't ripple, the air around you remains still. This is one of the greatest paradoxes of existence, the fact that everything in the universe seems to be in constant motion, but we experience none of it. From the smallest atom to the largest cluster of galaxies, everything spins, turns, or orbits in some way. Even the fabric of space itself may have a subtle rotation woven into it, a spin at the cosmic level. And yet, as we go about our day, we feel frozen in time. How can this be? If everything is moving, why do we feel so still? The answer, surprisingly, begins with inertia, a concept first described by Isaac Newton in the 17th century. Newton's first law states that an object in motion stays in motion unless acted upon by an external force. The motion we experience, or rather the lack of it, is explained by this principle. Think of it this way. You are not isolated from the Earth's rotation. You, the air around you, the ocean, the mountains, everything is moving with the Earth, all locked in sync. We don't feel the Earth spinning because, in a sense, we're not resisting it. There's no difference between us and the planet. It's a smooth, constant motion. To feel motion, you need a change, a shift, a push, a pull. But with the Earth's steady spin, there's no such change. We move seamlessly with it. This same effect is experienced by astronauts in orbit. They travel at a speed of 17,500 miles per hour, completing a full orbit around Earth every 90 minutes. Inside their spacecraft, everything feels still, despite their rapid speed. This phenomenon is called uniform motion. It's the same reason you don't feel the speed of a plane while cruising at 500 miles per hour. When the motion is constant, we don't notice it. And of course, the Earth is just the beginning. From the Earth's spin to the Sun's rotation to the Milky Way's vast spiral, everything is in motion. Even time itself is a result of this constant motion. The very rhythm of day and night, the changing seasons, and the very act of aging are all tied to the great cosmic spin. What if we could feel it? What would that do to our perception of time? Imagine being able to feel the Earth turning beneath you, the Sun's path across the sky, the galaxy's graceful spiral through the universe. It would be overwhelming, a sensory experience that could make time itself seem elastic, stretching, pulling, and bending with every spin. The trick, though, is that our senses were never designed to feel such vast motions. We evolved to sense smaller changes, like walking, running, or climbing, actions that involve a direct force. Our ears are built to sense the pull of gravity, not the smooth, constant glide through space. That's why you feel the acceleration of a car, but not its steady cruise down the highway. On Earth, we are constantly moving, but we're moving together with everything around us, and that is why we don't feel it. We've created tools to measure this motion, of course. The Foucault pendulum, for example, was designed in 1851 by Léon Foucault to demonstrate Earth's rotation. As it swings back and forth, the pendulum's direction gradually shifts, showing the Earth spin. It's a subtle movement, but when observed over a long period, it reveals the Earth's rotation without any need for complicated machinery or instruments. In space, this motion becomes even more fascinating. The Milky Way, our galaxy, turns once every 230 million years, carrying with it hundreds of billions of stars. Each of these stars, like our Sun, carries its own rotational momentum. In fact, even the Sun spins, but not uniformly. It rotates faster at its equator than at its poles, a phenomenon called differential rotation. This complex motion influences the Sun's magnetic fields, creating solar flares and coronal mass ejections that affect our planet's atmosphere. The Milky Way itself is just one of billions of galaxies spinning in the vast universe, each carrying its own signature of motion. The universe, according to some models, may even have a subtle global rotation that stretches across its fabric. This cosmic spin is woven into the very structure of everything, shaping galaxies, stars, and even the light that reaches us from the farthest reaches of space. But how did this all begin? If everything in the universe is spinning, what was the source of that motion? Was there a beginning to all of this? Or has the universe been turning forever? The question leads us into the heart of cosmology, where the universe's first moments after the Big Bang remain one of the greatest mysteries of all. Was the Big Bang the start of everything, or was there something before it, something that triggered the spin of all creation? The Big Bang, the moment in which the universe is thought to have come into existence, is often described as the origin of space, time, and all matter. But despite the poetic image of a sudden explosion, the reality of the Big Bang is much more complicated. It wasn't a simple bang in space as we often imagine. It was a rapid expansion, a sudden increase in the size of the universe from an incredibly hot, dense state. In the first fraction of a second, the universe expanded at a rate faster than the speed of light, an event known as inflation. During this period, space itself wasn't just expanding, it was stretching. Think of it like a balloon inflating, with galaxies acting as the dots on its surface. As the universe expanded, the energy that permeated everything began to cool, leading to the formation of the basic elements, hydrogen, helium, and traces of lithium. These elements would eventually come together to form the stars and galaxies we know today. But there's something truly remarkable about the Big Bang. It wasn't just an explosion, it was the beginning of motion itself. The very forces that shaped the universe were born in that instant. Gravity, electromagnetism, the strong and weak nuclear forces, they all began to operate from that moment forward, dictating the behavior of all matter. But what's even more astonishing is that from the moment of the Big Bang, the entire universe began to spin. This spin, this motion, was not uniform. It wasn't as if everything was rotating in one direction. Rather, the motion of the universe's formation was more like the swirling of a liquid or a gas. As matter began to come together, it accumulated into clumps that were rotating, swirling through space in the chaos of the early universe. Over time, these rotations became the building blocks of galaxies, stars, and planetary systems. In fact, this spinning motion is present in nearly every cosmic object we observe. Planets spin, stars spin, and galaxies themselves spin. The spiral shape of galaxies, such as our own Milky Way, is a direct result of angular momentum, the property of spinning objects that causes them to preserve their motion over time. Angular momentum is a law of physics that states that a rotating object will continue to rotate unless acted upon by an outside force. It's why the planets in our solar system continue to orbit the Sun, why the stars in the Milky Way continue to spin around the galaxy's center. So what caused the universe to spin in the first place? Why did the Big Bang not just create a static, expanding universe, but one that was set in motion, spinning with a force that has carried on for billions of years? The answer, it seems, is tied to the very nature of the universe itself, the way the early fluctuations in density during inflation caused a twisting, spiraling pattern to emerge. In the first moments after the Big Bang, the universe was incredibly chaotic. Tiny quantum fluctuations caused slight variations in the density of matter. These fluctuations were incredibly small, but over time, they grew. And as they did, the slight differences in density led to rotational movement, as gas clouds, dust, and particles came together under the force of gravity. They began to spin, and that motion became the foundation of the universe's structure. The formation of stars and planets. As the universe continued to evolve, the first stars began to form around 100 million years after the Big Bang. These stars were massive and short-lived, burning their fuel quickly and explosively. Their formation was influenced by the motion of the gas and dust in the early universe, which was still affected by the initial spin of the Big Bang. The swirling clouds of hydrogen gas collapsed inward under gravity, and as they did, they began to spin faster, much like a figure skater pulling in their arms during a spin. This spinning motion caused the gas to condense at the center, creating a dense core that would eventually ignite into a star. But even more fascinating, the spinning motion of these first stars helped to shape the universe's first galaxies. The stars didn't form in isolation, they formed in clusters, which eventually merged into larger rotating galaxies. As these galaxies formed, their stars continued to orbit around the galaxy's center, a motion that persists to this day. But the motion of the stars and planets wasn't limited to the early universe. Even in our own solar system, the sun, planets, and moons are all moving in ways that are a direct result of the initial spin of the universe. The planets in our solar system rotate on their axes, and they orbit the sun, all as a result of angular momentum. The motion of our planets, the way they interact with each other, is also influenced by the motion of the galaxy itself. Our sun orbits the center of the Milky Way once every 230 million years, carrying the entire solar system along with it in a slow, graceful spin. As the planets began to form around these early stars, they too started to spin. The forces that caused them to spin came from the initial motion of the universe and the gravitational forces acting on them as they formed. Planets like Earth, with their tilted axes, began to spin around their stars, creating the cycles of day and night that we experience. But the motion of these planets wasn't just limited to their orbits. Over time, the spinning motion of the Earth caused its axis to tilt, creating the changing seasons. The spinning of the Earth also played a key role in shaping the planet's weather systems. Winds, ocean currents, and even the formation of storms are all influenced by the planet's rotation. The ultimate fate of the universe. Now, as we look forward, we are confronted by the ultimate fate of the universe. The motion of galaxies and stars will continue for billions of years to come, but eventually, the forces of entropy and dark energy will take their toll. As the universe expands, galaxies will drift farther apart, and the once vibrant motion that shaped the cosmos will begin to slow. In the distant future, the Milky Way and Andromeda will collide. The spinning galaxies will crash together, their stars interacting in ways that will transform them into a new, elliptical galaxy. The supermassive black holes at the centers of the galaxies will merge, releasing an immense burst of energy that will echo across the universe. But even after this cataclysmic event, the galaxies will continue to spin, forever trapped in the dance of motion. Yet, even as stars die and galaxies fall apart, the universe's spin will never truly end. It is the most fundamental force at work in the cosmos, the force that keeps everything moving, that creates the cycles of birth and death. The universe is a vast, eternal motion machine, and even when everything is dark and still, the motion will continue. As the universe continues its eternal spin, the vastness of its motion becomes clearer, not just in the immediate moment, but as an enduring force that stretches across time itself. The galaxies, stars, and planets we observe today are not static. They are moving within the vast web of cosmic forces that shape them. And while we are mere specks in this grand, ever-changing dance, understanding the rhythms of the universe reveals a deeper truth. Everything moves, everything spins, and everything eventually fades. Looking deeper into the grand scale of the universe's motion, we see that the galaxies themselves are not only spinning, but also migrating. Each galaxy in the universe is like a boat on the cosmic ocean, subject to the current of dark energy, the mysterious force accelerating the expansion of the universe. The Milky Way, for instance, is not merely stationary in space. It is constantly moving toward the Andromeda Galaxy. In about 4.5 billion years, the two galaxies will collide and merge into a new, single elliptical galaxy. This event will reshape everything we know about the universe's structure, scattering stars into new orbits and possibly triggering the formation of new stellar clusters. However, the collision of galaxies is far from a cataclysmic end. It is a transformative event where the interaction of two galaxies creates new stars, new planetary systems, and new chances for life. In the aftermath of the collision, the black holes at the centers of each galaxy will likely merge as well, releasing enormous energy in the process. This violent union of forces will change the course of the galaxies, but not in a destructive way. It is simply the inevitable next step in the universe's motion. What's more fascinating is that while these events take place on a cosmic scale, they are driven by the very forces that govern the smallest aspects of the universe: gravity, angular momentum, and the relentless pull of dark matter. Gravity binds galaxies, stars, and planets together in an intricate cosmic dance. As each galaxy spins, gravity shapes the structure of the universe, drawing objects together, bending light, and influencing the orbits of stars and planets. The spinning of these galaxies creates a dynamic, ever-changing landscape that allows new stars to form and old ones to die. Of dark matter. One of the greatest puzzles in understanding the universe's spin is the enigma of dark matter. We know that dark matter makes up approximately 85% of the mass of the universe, yet we can't directly observe it. We can't see it, hear it, or touch it, but its gravitational effects are undeniable. It is the glue that holds galaxies together, the invisible hand that ensures they continue spinning smoothly. Dark matter, which doesn't emit, absorb, or reflect light, doesn't interact with electromagnetic forces in the way regular matter does. So how do we know it exists? The answer lies in the way galaxies behave. When scientists observe the movement of galaxies, they see that the outer stars are rotating at a speed much higher than expected. According to Newton's laws, they should be flying off into space due to the lack of visible mass to hold them in place. Yet, they don't. The only explanation for this anomaly is that an invisible mass, dark matter, is exerting an additional gravitational force, keeping these stars in their orbits. As the universe spins, dark matter's influence shapes the galaxies, keeping them intact and influencing their motion. The presence of dark matter not only stabilizes galaxies, but also affects the movement of galactic clusters. The Milky Way and Andromeda are part of a small group of galaxies known as the Local Group, and this group itself is being drawn toward a larger, even more massive concentration of galaxies called the Virgo cluster. Dark matter is the driving force behind the motion of galaxy clusters, ensuring that even in the vast emptiness between galaxies, gravity will pull them together. But dark matter is not the only invisible force at play. There is also dark energy, the mysterious force behind the accelerating expansion of the universe. While dark matter holds galaxies together, dark energy pushes them apart, creating an eternal tug-of-war that defines the universe's future. The fact that the universe is expanding faster over time suggests that dark energy is becoming increasingly dominant, threatening to tear apart galaxies, stars, and even atoms themselves in the distant future. In a way, the universe's motion is a balance of opposing forces. On the one hand, gravity, fueled by dark matter, brings galaxies together. On the other hand, dark energy pushes them apart. These forces are constantly at odds, shaping the universe's evolution. The push and pull of dark energy and dark matter create the conditions that govern the motion of galaxies, the formation of stars, and the fate of the universe itself. The final stages: entropy and the heat death of the universe. As the universe continues to expand and spin, it is slowly heading toward its final fate. In a sense, the universe is slowly running out of energy. Stars burn out, galaxies move farther apart, and the universe cools. This process is driven by the second law of thermodynamics, which states that entropy, or disorder, always increases over time. As entropy increases, the energy available for doing work decreases, meaning that stars will eventually exhaust their fuel and fade into darkness. In the distant future, after all the stars have burned out and the galaxies have drifted too far apart to interact, the universe will reach a state of maximum entropy. The energy once used to power stars and galaxies will be spread thin, and the universe will be cold and dark. This is the heat death of the universe, a state of thermodynamic equilibrium where no processes capable of performing work remain. The universe will be an infinite void where nothing changes, nothing moves, and everything is in a state of perfect uniformity. But even as the universe fades into darkness, the forces that began with the Big Bang will continue. The galaxies, stars, and planets may vanish, but the spin, the motion, will persist. Whether it's the faint spin of dark matter or the relentless pull of black holes, the universe's motion will continue on, even as everything around it fades away. The motion, the cycles of creation and destruction, will endure long after the last star dies. The ultimate end of the universe is a state of stillness, a cosmic silence where nothing moves, nothing changes. But even in that state, the motion of the universe's origin, the Big Bang, will echo through time. The legacy of the motion that began with the birth of the universe will continue to shape the cosmos, a reminder that even in the absence of stars and galaxies, the dance of space and time will never truly cease. As the universe ages, the inevitable fate of its stars and galaxies becomes increasingly clear. The death of individual stars and the slow but relentless spreading of the galaxies are signs of a universe on the verge of eternal stillness. But this isn't the end yet. It's the slow burn of a cosmic cycle that, for now, is still full of motion and change. Within the Milky Way, the supermassive black hole at the galaxy's center, Sagittarius A*, continues its quiet, powerful work. Black holes are not merely destructive forces, they are creators in their own way. As stars venture too close to their immense gravity, they are consumed, their remnants often becoming the raw material for new stars and nebulae. These cosmic collisions and births create an intricate dance that spans millions of years. However, the energy required for these processes is becoming scarce. The stars that once filled the galaxy with light are burning out one by one. The nuclear fusion that powers these stars is slowly reaching its limits, and new stars are becoming rarer. In the outskirts of the galaxy, the rate of star formation has dropped dramatically. Nebulae, the stellar nurseries of the Milky Way, are beginning to fade, their gas and dust dispersing into the void. One of the most intriguing aspects of the Milky Way's future lies in its halo, the vast region that extends beyond the main disk of the galaxy, composed of ancient stars and mysterious dark matter. This halo is far from empty, though. Recent discoveries have revealed that some of the oldest stars in the Milky Way's history reside in this distant region. These stars are relics of a time when the universe was young, and their presence in the galaxy's outskirts is a testament to the galaxy's long evolutionary journey. The stars in the Milky Way's halo are dying slowly, their lifespans measured in billions of years. As they fade, their final remnants will be absorbed by the black hole at the galaxy's center, adding to the growing mass of the singularity. Sagittarius A*, over time, will become a massive engine of destruction and creation, consuming the remnants of the old stars while simultaneously preserving them in a different form, recycling the material into something new. But eventually, even the black hole will reach its limits. The gravitational forces within it will become so immense that the very fabric of space-time will be torn apart. The quiet march of entropy. While the stars and black holes continue their cycles, there's an even more insidious force at play: entropy. This second law of thermodynamics ensures that the universe is slowly moving toward a state of disorder and decay. As stars burn their fuel and galaxies collide, the organized systems of matter will break down into randomness. This process is relentless, and every passing moment edges the universe closer to its inevitable heat death. Entropy can be seen in every corner of the cosmos. It is the slow unraveling of structure, the dissolution of once stable systems. Even the galaxies that once formed orderly clusters are now drifting apart. The push from dark energy, which is causing the accelerated expansion of the universe, is forcing galaxies to race away from one another at increasing speeds. The vast distances between galaxies will eventually become so large that any trace of one galaxy's light will be lost to another. The universe will become a cold, dark place, with stars long gone and galaxies too far apart to interact. The end of the universe, according to the theory of entropy, is a state of perfect equilibrium. There will be no more stars, no more light, no more galaxies. All that remains will be a dark, homogeneous space filled with remnants, black holes, white dwarfs, neutron stars, and the occasional wandering rogue planet. The energy that once fueled the stars will be spread thin across the universe, and the last remnants of heat will fade into the infinite void. However, before this ultimate fate is realized, the final stages of the universe will be marked by one final spectacular event: the evaporation of black holes. For a long time, it was believed that black holes were permanent features of the universe. Once formed, they could only grow by absorbing more mass. But in the late 20th century, physicist Stephen Hawking proposed that black holes actually lose mass over time through a process now known as Hawking radiation. According to this theory, black holes gradually radiate energy in the form of particles, causing them to lose mass and shrink. Over an unimaginably long period of time, this process will cause black holes to slowly evaporate, leaving behind only radiation and empty space. This phenomenon will play a crucial role in the ultimate fate of the universe. As black holes evaporate, the final remnants of mass and energy will be released into the surrounding space, creating a final burst of radiation before the universe settles into the cold stillness of heat, death. The final generation of life. While the universe moves toward this inevitable fate, life, at least in the form we understand it, will also face its own extinction. On Earth, life has already undergone countless changes since its origins. From single-celled organisms to the complex human civilizations we see today, the story of life is one of adaptation and survival in an ever-changing environment. But Earth, too, will eventually be impacted by the larger forces at play in the universe. As the Sun continues its aging process, it will begin to run out of fuel. In about 5 billion years, the Sun will exhaust its hydrogen, causing it to swell into a red giant, consuming the inner planets, including Earth. This will mark the end of life on our planet. After the Sun sheds its outer layers, Earth will become a frozen, lifeless rock, drifting through space. But even as Earth's fate is sealed, life may have already spread elsewhere in the galaxy. One of the most tantalizing possibilities of our time is the idea that life could have developed on planets orbiting stars far older than our own. These hypothetical civilizations might have developed technologies far beyond our own, extending their lifespans and possibly even discovering ways to survive as their home star began to die. Perhaps these civilizations, knowing the inevitable fate of their home galaxies, have already developed methods of escaping the heat death of their own stars. And while life on Earth may be extinguished, the possibility of life elsewhere in the universe persists as galaxies and stars continue their cycles of birth and death. Maybe in some far-flung corner of the cosmos, life continues to thrive, shielded from the decay and eventual destruction that the rest of the universe will face. Or perhaps, like everything else, it will eventually fade, lost to the relentless pull of entropy. As the universe continues its slow march toward entropy, the final act of cosmic drama unfolds, not with an explosion, but with an unremarkable quietness, a stillness that stretches across the vastness of existence. The stars fade, galaxies dissolve into the void, and the fabric of reality, once so rich with energy and life, dissipates into a peaceful darkness. In this final era, the last galaxies, like the Milky Way, are scattered throughout the cold emptiness of space. The black holes that once ruled the hearts of galaxies now rule the universe's destiny. They are the last great forces in the cosmos, slowly, inexorably consuming everything in their path. But even black holes, with all their immense power, are not immortal. Their power wanes, their energy bleeds away over billions of years, until they too begin to lose their grip on the universe. Hawking, radiation, the process that causes black holes to lose mass and shrink, becomes the universe's final, quiet death knell. The stars that once illuminated the heavens, the black holes that devoured them, and the galaxies that held them all together, everything is winding down, slowly and methodically, like a clock running out of time. The last vestiges of matter are scattered throughout an ever-expanding universe, devoid of warmth, of life, of motion. The black holes, having consumed everything they could, continue to shrink, their event horizons slowly dissipating until they too vanish, leaving behind only the faintest remnants of their existence, the cosmic radiation, the faint flickers of once great cosmic forces. The universe becomes an empty, lifeless expanse, devoid of stars, planets, galaxies, or any traces of the vast drama that unfolded across the ages. In the final moments, as the universe approaches its heat death, there's a sense of eerie tranquility. No longer are there stars to look up at, no more gravitational forces shaping the paths of celestial bodies. The once vibrant motion of galaxies, spiraling and twirling in the vast ocean of space, is now but a distant memory. The energy that once powered the birth and death of stars, the cosmic forces that shaped the galaxies, are now reduced to nothing more than a faint hum, a whisper in the cosmic silence. The end of time itself. And in this silence, time itself begins to lose its meaning. As the universe expands further and further, the once clear passage of time becomes indistinct. The idea of past, present, and future fades, because in a universe where nothing changes, time cannot flow. What was once a progression, a continuous march forward, becomes irrelevant. Without stars to mark the passage of days, without galaxies to measure the evolution of the cosmos, time collapses in on itself. This is the endgame of all things, the culmination of billions of years of motion, growth, and decay. The universe, which once roared with creation, has slowly come to a halt. Life, once flourishing on planets, has long since extinguished. The forces that created and shaped existence are now quiet, having burned through their energy, leaving only a peaceful, empty void. The last gasps of energy radiate away in the form of cosmic background radiation, but even this will fade with time. The universe, as we once knew it, no longer exists. The cosmos has transitioned from a place of light and movement to a place of stillness and silence. What was once a vibrant web of interconnected galaxies, stars, and cosmic forces has become a barren, empty expanse. The grand cycle of birth, death, and rebirth that once defined the universe is no more. The universe's final state is one of perfect equilibrium, one where no energy, no life, no force remains to change or shape the emptiness. The legacy of existence. But even in this final silent death, there is a subtle, lingering sense of continuity. The universe, for all its eventual stillness, will leave behind something. The echoes of its creation will persist in the very fabric of space-time. The ripples from the birth of galaxies, the explosive deaths of stars, and the quiet consuming of black holes will be recorded in the cosmic memory, woven into the very structure of the universe. These remnants, small traces of the past, will echo throughout eternity, marking the once vibrant dance of cosmic life. The story of the universe, as it unfolds and unravels, is a testament to the endless cycle of creation and destruction. It is a story of motion, of forces constantly at play, of the birth of stars and the death of galaxies. It is a story of life, energy, and change, a story that continues even after the lights go out, even after the galaxies are scattered and the stars have burned away. And perhaps in some distant future, when the universe is nothing but an empty shell of its former self, the echoes of that story will linger, carried on the faintest particles of light and radiation, reaching across the void, a reminder of the cosmos that once was. The infinite rebirth. As the universe drifts further into darkness, some cosmic theorists speculate that the universe could eventually enter a state of infinite rebirth. In the far, far future, as everything winds down and the last black hole evaporates, new conditions may arise, conditions that could spark a new Big Bang. Perhaps the remnants of the previous universe, caught in the cyclical nature of space and time, will give rise to something new. Though it's impossible to know for certain, some believe that the death of one universe could lead to the birth of another. The vast, empty space that remains could serve as the seed for a new creation, a new cycle of galaxies, stars, and life. The idea of a big bounce suggests that the universe may never truly end, but instead experience a continuous cycle of expansion, collapse, and rebirth. While the current universe will eventually fade, it may not be the final chapter. The cosmos may continue to reinvent itself in an infinite loop, an eternal dance of life, death, and creation that never truly ends. For now, though, the universe as we know it fades into the stillness. It is a vast, empty silence, a reminder of the beauty of what was and a hint at the possibility of what might come next. The universe, forever spinning and expanding, will continue in some form even when the last stars have burned out. Its legacy lives on in the endless spin of time and space. The end.